Okay, good evening, everyone. So we'll be starting the session in about a minute so that let others also join. Okay, so let us start our session. Already 6:05. So yeah, okay. Hi. So my name is Varnit Kapoor, and welcome to the week 7 tutorial of the course CFD using Finite Volume Method. And till now in the week 6, we have dealt with a lot of things, and the last topic was about the unsteady. We were solving of the unsteady diffusion equation, and we were towards the end of like placing all the terms together. So let us again write down that equation. So the equation was something like this: rho I p pp minus rho of pp naught into del v is equal to delta t into f is that vector which we have already discussed. Summation of gamma grad p of the faces dot product with AF plus 1 minus f, we write it here, plus 1 minus f into summation of grad phi of all the faces at 0th step and step AF, okay, plus del V del T F, the source term SP 5 PP plus 1 minus f, and let's write here, plus 1 minus f SC plus SP 5 naught. Okay. Now if you pick out the terms of IP naught and separate it out, okay, so your equation will come down to some neighboring points. So let us write down the equation. If you see this term, the 5p naught, the vector f 1 minus f, and this term f and 1 minus f. Okay, right. So if I take out the 5p term here, 5p rho del v on del t plus f of summation of a and b neighboring all the neighboring points minus f into the source term sp del v is equal to, mix the 5p naught rho del v over del t. You can refer to the last tutorial. We have already towards the end of the this equation. Okay. So you have to check out the last tutorial and watch the lecture videos as well. Okay. Plus F factor summation A and B neighboring points, I and B neighboring coefficients, plus 1 minus F summation of A and B, I and B not, plus vector into SC plus 1 minus F into SC naught plus SP naught 5 naught del V. Okay. So this equation looks like something. AP phi P is equal to summation of neighboring coefficients into F phi NB plus 1 minus F phi NB naught. Okay. Phi NB naught plus AP minus 1 minus F summation of A and B phi P naught plus P. This is your equation, final equation. Okay, where AP naught is nothing but rho del V over del T. AP is AP naught minus F SP del V plus F summation A and B. And your D is F SC plus 1 minus F SC naught plus SP naught PP naught del V. Okay. Your A east is gamma east del Y over del XC, and A naught will be gamma N del X over del YN. Okay. Now, there are three different cases. When this factor will be completely zero, the factor F, when F is 1 and when F1 time F is half. Okay, there are three different cases which we'll deal with. Okay. The first case is the explicit scheme. Okay. Explicit scheme. Where your factor F will be 0, where your factor F will be 0. That is, F is equal to 0. So now put F is equal to 0 in the above equation, this equation. Okay. So the equation will become like AP phi P is equal to summation of A and B phi and B naught plus AP minus summation of A and B phi P naught plus B. Okay. Where AP and AP naught will be AP is equal to AP naught, both will be equal if you observe, because your AP naught, as this term goes to 0, this term goes to 0, because F is 0. So that will be, both will be equal, which will be equal to rho del V over del T. And your B will be SC naught plus SP naught phi P naught del B. Okay. All right. If you have any doubts, you can ask me, and else you should refer to your lecture videos as well and the previous tutorials as well. So this equation, if you see, observe here, so what looks like the RHS in this equation. RHS in this equation is completely known or unknown. It is known because you know the values are this previous time steps. Okay, these values are known. The values of phi p at t plus delta ten p can be found. This value can be found because RHS is completely known. Okay. Next, by substituting the phi values at the previous time step in the RHS. then there is no need to solve the system of linear equations, that is Ax is equal to b, because you directly know the values at this point and this point, that is at t is equal to 0. You put the values, RHS is known, you get the values at directly at t. Okay. Then Scarborough is not relevant here because there is no need for solving the equations. There is a summation of a and b over ap is less than 1 is not necessary here. Because directly the values are known, you can get that. And when the steady state will reach, that means your ap should approach to 0. All right. So if you observe, this will become summation of a and b phi and b naught is equal to what it should be, plus this term should be equal to this. Okay, should be equal to this. Okay. These are some comments already been dealt in the lecture videos. I'm just giving you a brief once again. And this property should always be satisfied by any time stepping scheme, because whatever time step scheme you are using, this property will always be used. And here the order of accuracy will be first order accuracy. First order accuracy. All right. It is simple and convenient because you don't need to solve the linear equations. Simple and convenient to use. However, there is a restriction over the time step. That is a drawback. And we'll get a conditional stability here. So delta t cannot be arbitrary here. You have to take a particular value. Okay. We will see the stability analysis of time steps in later part of the tutorial. Don't worry about that. Okay. Any doubts still here? So one way is if you observe this AP5P, this equation highlighted at orange. So delta t cannot be any arbitrary value. Okay. And one thing is that this value, the coefficient should always be positive. Okay, because if it is a negative value, the coefficient is a negative value, and as with the time, the previous time step, phi p value increases, this whole value get decreases. Because of that, phi p decreases. That is not acceptable. That is not acceptable. It's not good. So you always want this value to be positive, but it is not acceptable in the context of parabolic PDEs. We have seen what are parabolic PDEs and all. That means AP is less than summation of A and B phi p, A and B, okay, is not acceptable. Otherwise, it will give a negative value. Negative value will give a negative value. With an AP naught, it should be AP naught. Otherwise, it will give negative, leads to negative coefficients of coefficients of IP. That means if this value increases with time, this value will decrease. So that is why this is not acceptable. Okay, for the parabolic function. So that means we should always have, therefore, AP should be always greater than equal to summation of A and B. Okay? Should always be greater than equal to A and B. And for a uniform mesh with constant properties, or a uniform with constant properties, there is a delta time t restriction, time step restriction, which I have taken rho del x square by 2d gamma. So we will see the proofs and everything of this, how it came. So where d is 1, 2, 3, depending on the dimension. Depending on the dimension of the problem. Okay. So we will see it from the von Neumann stability criteria. This thing, you will see this in today's tutorial from von Neumann stability criteria. Okay. So that means delta T is of dependent over del x square. Okay. So delta T as del x changes, the delta T changes its square time. So it's a restrictive in nature. Time step restriction is happening here. Time step restriction. So as delta T decreases, delta x decreases, delta T decreases much faster. Delta T decreases much faster. Okay. So in steady state problem, if you use this explicit scheme, is it computationally cheaper or not? Why we use like other schemes if you are not going with the, because it's an unsteady case which we did. So why we do deal with the steady state equations basically? Earlier we have seen all the steady state equation. Here we are seeing the unsteady equation. This is an unsteady equation. So you have to think about that and get to the point that is the explicit scheme if we use this computation is cheaper or not. Okay. Now let's come to the fully implicit scheme. Next case, fully implicit method, where your f will be equal to 1. Equal to 1. If you put back that f in that equation, you will get the equation f as 1, and you will get the equation as a and b, I and b plus ap naught, ip naught plus b, where your b is fc del v and ap naught is rho del v over del t, and ap will be summation of a and b plus ap naught minus sp del v. This will be our equation. So every delta t need to solve a system of linear equation this time. There is need to solve the system of linear equation because there are all the values on the right hand side are not known this time. You cannot directly put and get the left hand side value of. Okay. All the these are not available. Here it is unknown. Okay. This is known, but that is unknown. So you have to solve the system of linear equations. And if you go with the in the absence of source, if source term is 0, this term is 0, then you are left with this is equal to this. Okay. So you can say that it is bounded. Okay, bounded as well, which is just summation of neighboring coefficients. So phi b is bounded between phi p naught and phi n b, so all the neighboring values. So implicit schemes satisfy the property of boundedness for parabolic PDEs. This is an advantage. So any large delta t can be used, but accuracy guarantee is not sure. Okay, guarantee is not there for the accuracy in this. The method is only good for order of delta t. That is a first order method. And also you can say that values of t plus delta t prevail over the entire delta t. Everything has been discussed in the lecture. I'm just giving a brief about that. What has happened? All. We have discussed so far unsteady diffusion equation and derived a general time-stepping scheme. Okay. All right. That was our equation. Now, if we go with another kind of vector, we have seen the explicit scheme, we have seen the implicit scheme. Now, if I go with a factor of 0.5, that is mix of both of them. That is nothing but a Crank-Nicolson scheme. Crank-Nicolson. Crank-Nicolson. Where f is nothing but 0.5. If you put back 0.5 there, what you will get? AP phi P is equal to 0.5 into summation of A and B, phi and B plus phi and B naught plus AP naught minus 0.5 summation of A and B, phi P naught plus B, where B is nothing but 0.5 into SC plus SC naught plus SP naught phi P naught del V, and AP is AP naught minus 0.5 SP del V plus 0.5 summation of A and B. Summation of A. All right. Now, there is a need to solve the system of linear equation. Again, right hand side is not known completely. Algebraic equation need to solve at every delta t. Then if you see here, this coefficient cannot be again negative. We have seen this. Option should always be positive. AP naught should be greater than equal to 0.5 times of. Okay. Then this scheme is second order accurate in time. You'll see all these things about the order of accuracy of with time and space. We have to choose the delta t wisely so that we can make the error go down quickly compared to the other schemes. And in the Crank-Nicolson schemes, it makes a linear approximation. Okay, that is from this point to this point. You are taking a linear approximation of using the factor of half between t and t plus delta t values. So there is a truncation error. Different kind of errors can be there. So we have to quantify truncation errors can be because of the profile assumptions, or we have to quantify these truncation errors. All right. So in steady diffusion cases, there is only a spatial truncation error. Whereas in unsteady diffusion, we have spatial as well as temporal truncation errors. Whatever that order of delta t or order of delta x we are dealing with, those are the truncation errors we are taking. Okay. Let me write the heading. Truncation errors for steady diffusion. We have spatial with space only truncation error. And for unsteady diffusion with space as well as with time, spatial and temporal truncation. Okay. Let's come to first steady diffusion. Steady diffusion. So what was our equation? We have seen this equation a lot of times. Del dot gamma rho of any property phi plus source term is equal to 0. So what are the approximations here? What are the assumptions? First, assume that the mean value of the source term, that is S. Then you write it first. The source S of phi dV. When you do this, you assume that it is S of phi at point P del V. So the mean value of the source term is represented using the self-centered values. You assume that mean value of source term is represented using the cell centroid value. Mean value approximation is happening here. Then when you deal with gamma grade phi of east, so it is taken to be the value at the face centroid, okay, not for the complete set. Okay, that is another assumption which you deal with. Second is leads to the truncation errors in state diffusion case. When you deal with gamma grad phi of east, you say that is taken to be the value of at the face centroid. And then you say, so one mean value approximation and gradient approximation has happened. Then you say dou phi by dou x of east. You write it as phi of east minus of phi of p over del x of east. So it is a linear profile assumption you make here. Linear profile assumption. Linear profile assumption. So coming to the mean value approximations for 1D uniform grid, if we come up with that. Mean value approximation. So it's a 1D uniform grid if I'm taking 1D uniform grid. So divided in three parts, uniform grid. This is your point P. This is your node W and east. Okay. This is your west face. This is your east. This is delta X. This is also delta X. Okay. Delta X and delta. So this is your X direction. Now, if you do for any property phi of X being diffused. Now, if you do the Taylor series expansion here, Taylor series expansion. Taylor series expansion. Phi of X of phi of X about phi P and rho phi by that, okay, at the point P, which you are doing the Taylor series expansion with respect to the node P. So phi of X can be written as phi of P plus X minus XP into dou phi by dou X of P plus X minus XP whole square by 2 factorial to 2 phi by dou X square about P and Just a simple Taylor series expansion we are doing. Now you have to integrate the above equation. Integrate over a control volume. To integrate phi of x dx, because dv is equal to dx in one dimension. So from x west to x east. This complete cell has x west to, for this control volume, x west face to x east. Okay. Which will be equal to, the right hand side of the expansion will be x west to x east by p dx, okay, plus again x west to x east x minus xp dou phi by dou x dx plus x west to x east, that will be x minus xp whole square by 2 factorial dou 2 phi by dou x square about p dx. Okay. So what can I write this first term? This first term can be written as x west to x east phi p dx can be written as phi p is as it is, and integration of 1 dx is x, so that will be x east minus x west. So that is phi p del x, phi p del x. All right. Now the next term, x west to x east, x minus xp, this term. Okay, x minus xp dou phi by dou x about p dx. Let us take some change the variables. Let us write t as x minus xp. So dt will be how much? Dx. So for west phase, when xw is there, that means tw will be xw minus xp. W minus xp. And x east is there, so t east will be xe minus xp. P minus xp. All right. I guess that's clear. So it will be written as integral limits. This gradient can be taken out, dou phi by dou x at p, x minus xp is t, and dx is dt. Okay. So limits will be from minus del x by 2 to del x by 2. So this can be written as dou phi by dou x about p. If you see, this is minus del x by 2, this is plus del x by 2. So integration of t is t square by 2 minus del x by 2 over plus del x by 2. Even function, this integration should come out to be 0 for the even function. Now, into the next term, x west, x east, x minus xp whole square by 2 factorial, dou 2 phi by dou x square about p dx will be minus del x by 2 plus del x by 2 dou 2 phi by dou x square. Again, take those dt square by 2, t square by 2 over dt. Integrate this. T square integration will be t cube by 6. So it will come out to be something like rho 2 phi by dou x square about p del x cube by 20. Del x cube by 20. Now put all these things in the equation, back in the equation. So you will get the term as xw to x east phi of x dx. The first term was phi p del x of the Taylor series expansion. Second term was 0. Third term you have got something order of del x cube. Okay, order of del x cube. Now you divide by del x, divide by del x, what you will get? You will get for the mean values phi of x dx by del x is equal to mean value, which is equal to phi p plus order of del x square, and its gradient dou to phi by dou x square about p. So you see the neglected term is, this is the second order accurate. Okay. So we get the exact value if S is constant, but if S is linear, that is function of S, then you can say that dou S by dou X will not be zero in that case. I hope there are no doubts still here. Manoj, do you have any doubt? Okay, unmute yourself. Any doubts? Okay, mic issue. Do you have any doubts or not? You can type it in chat box. No doubts? Okay. All right. If it's clear till here, I guess we can proceed further. Right? Okay. We have seen order of accuracy for this case in spatial variations. Now coming to the non-uniform mesh. If you come with a non-uniform mesh, what you will observe compared to the uniform mesh. Just wait for a minute. Okay, let's come to the non-uniform mesh part. Non-uniform mesh. Suppose your mesh is something like this. This, like this. This is your point P, this is your base node, east node. Now this time, these will be different. Del XW, this is del XP, and this will be del XE. Okay. So mean value approximation is second order accurate even for non-uniform meshes here. Okay, let's see. So if you see here, gradient approximation. So if you have a non-uniform mesh, the mesh looks like this. Okay, so we have a cell one there, another cell here, something looks like del XW, del X east, all will be different. But the cell width of each cells are different, but the limits of integration will be same. That is minus because it is at the center itself. So this distance and this distance will always be because P is at the center. So minus del X by 2 to plus del XP by 2 will be equal to same equidistance within the cell about the center. So mean value approximation will still have 0 for the first derivative. The first derivative which we did, this value will always be 0. Will always be 0. But the second, so it will be a second order accurate. That means there is not going to be this term this time. So there will be this term, and you will divide by delta x. So it will be left with delta x cube. Okay. That will give you a second order accuracy. Second order accuracy. Right. So let us do the gradient approximation. So dou phi by dou x east will be phi e minus phi p over del x e. Now let us expand this phi east and phi p about phi east. Okay. Expand phi of east and phi of the p about phi e, small phase e. Phi e will be phi small e plus del x by 2 dou phi by dou x of east plus del x by 2 whole square by 2 factorial dou 2 phi by 2x square of east and so on. And phi of e will be phi of east again. This time it will be minus del x by 2 dou phi by dou x of east plus del x by 2 whole square by 2 factorial dou 2 phi by dou x square about east and so on. This will be minus 2 minus of east and so on. Okay. Now I should do the subtraction phi p minus phi e because that is what you want, phi e minus phi p. So what you will be left with? So phi e minus phi p will be first term will cancel out, second term will add up. That is delta x by 2, delta x by 2, 2 times is delta x of east. Next term will cancel out. Then some order of del x cube will be coming. Okay. And so on. Now divide by delta x both sides. So you will get phi e minus phi p by delta x. So phi by dou x of east plus order of delta x square. Delta x square. So we got the gradient approximation of dou phi by dou x of east as second order accurate because the remaining truncated part is second order. Similarly, above you got for phi, when you were solving for phi, it was your how much order accurate? You see, it was again second order. Okay. Any doubts still here? Just observe once. Just watch. Okay. Both of them are second order for uniformation, non-uniformation as well in spatial. Second order accurate, steady diffusion equation is also second order accurate for uniformation. Non-uniformation gradient calculation is first order. Okay. Notes. Let's come to the unsteady diffusion equation for truncation errors calculations. Unsteady we will do evaluation truncation rule. Evaluation truncation truncation rule. All right. So here rho phi p at because it's unsteady at next time step plus original time step, previous time step phi p naught, phi p1 and phi p1 naught. That is t plus delta t and t represented by cell-centered values. Okay. Then again source term was also taken be of cell-centered values. Gamma gradient of phi was face-centered values which you took okay during the assumptions. Then source term and gamma grad phi, the values are t plus delta t prevail over the entire time steps. Okay. Prevail over the entire time steps. These are the assumptions which you dealt earlier as well. But this is for unsteady. That we dealt for steady. Let me write all these terms. First thing, rho phi t at 1, that is t plus delta t, and the rho phi p at naught, that is t, represented by cell-centered values. And second, first term S is also cell-centered value. The term gamma grad phi at the face, okay, is taking face-centered values. Okay. In the unsteady diffusion evaluation for the truncation error, the assumptions which we have made, we are dealing with that only. So there is no convection term, only diffusion term, unsteady diffusion equation. We had some source term that was evaluated at the cell-centered value. We have the face-centered values for gamma grad phi. Okay. If you look the unsteady term rho phi p1 and rho phi p naught, these correspond to t plus delta t and t values. These are the representative of time. So cell-centered values, that is phi p, which we have used, are represented by cell-centered values, cell-centered values. And if you move to the other term, source term, that will see it is again dependent on cell-centered values and phase fluxes. These phase fluxes are represented using phase-centered values. These are the assumptions. Then we did the linear profile assumptions. Okay. for diffusion fluxes as well as the source terms for T naught and T plus delta T that we have made. These will depend on the type of the scheme which we are using. Either T naught prevail over the time entire delta T or T plus delta T prevail over the entire time set. Okay, these are the assumptions. Third one is source term and gamma grad phi of phase. The values are T plus delta T. Prevail over the entire time step. Okay, prevail over the entire time step. Any doubts? These are the assumptions which we have made. So again, we want the mean value approximations. So we can say that source term S bar and this grad gamma grad phi, if we are using an implicit scheme, that is a fully implicit scheme, then the values are T plus delta T prevail over the entire time step. We have made any other approximation in discretizing this equation. We have an unsteady term and the diffusion term and a source term. So both of them either we say that prevail over T values or T plus delta T values over the entire time step. And if you consider an implicit scheme, it is the T1 value, that is T plus delta T. So let us evaluate each of these approximations. So the first approximation is rho phi P1 and rho phi P0. Rho phi P1 and rho phi P0 represented between the cell-centered values. So what will be the order of the accuracy of this term? That is basically a mean value approximation. So we have already seen that mean value approximation, second order. In the space, this will lead to a second order in space because phi p is that we are looking at. It is delta x square in space, mean value approximation we have seen. Then the second assumption, S bar and gamma grad phi. This is also mean value approximation. We are calculating the integral SdV with S times delta V. So it's basically SdV representation. It's again a centered value. So again, it's a special order of accuracy, second order we have seen. Then the third one is about time. So this is basically what we will talk about if we have a source term or if we have a diffusion flux in the third term. Source term and the diffusion flux. These will incur some kind of temporal order of accuracy. First two are spatial order of accuracy. So that is what we are going to see now. Let's come. If I do S bar dt from T to T plus delta T for delta T, that is an average value, mean value. S naught is the value at time T and S1 the value at time T plus delta T. In the implicit scheme, we will expand S about S1 because it will prevail over T plus delta T. Factor is F is 1 there. Implicit scheme. Expand S about S1. Let us use the Taylor series expansion. S will be S1 plus 2S by dou T at 1 into T minus T1. T minus T1. Okay. Plus dou 2S by dou T square at 1 T minus T1 whole square by 2 factorial, and so on. So this is our Taylor series expansion about T1. Now, if you integrate from T naught to T1, that is T to T plus delta T, that is S dt, is T naught to T1, that is S1 dt plus T naught to T1, 2S by dou T, T minus T1 dt plus T naught to T1, dou 2S by dou T square, T minus T1 whole square by 2 factorial dt and so on. Okay. All right. You have to see the truncation error in time, basically. Again, if you do, it will be S1 delta T, 2S by dou T. So will be 2S by dou T at T1 at 1 into minus del T by 2 and so on other terms. Delta T, sorry. If you change the variable and do that. So now you divide by delta T for the average value. So T naught to T1 S dt by delta T is equal to S1 minus del T by 2 factorial, that is nothing but 2 only, 2S by 2T at 1 and so on. If you see, this is order of implicit scheme as first order accurate. We wrote above, now we have proved first order accurate. This is the truncation error in time. Implicit scheme, first order accurate in time, second order accurate in space. Implicit scheme, first order accurate in time, and for uniform mesh, will be second order accurate in space. Second order accurate. Any doubts? Clear? And similarly, you can deal for explicit and technical scheme. You can do for on your own as well. Okay. So in explicit, it will come out to be first order accurate, and in Crank Nicholson, the second order accurate, both in time. Now let's come to the stability of the scheme. Stability of the schemes. That is von Neumann stability analysis. Von Neumann stability just give me a minute. Okay. So now we are going to look at the proper analysis, that is the von Neumann stability analysis, where we are looking at the stability of the time stepping schemes. Okay. So this is a classical method that can be used to check the stability of the time stepping schemes we have. This can be applied if you have simple 1D problems with zero source term and without any non-linear descent things. Okay. So essentially, it tells us through the stability analysis, if we have a time stepping scheme, the time step that we are choosing to keep the round of error stable or not, that is the stability analysis stage. So round of errors comes from going from time step to time steps. In computers, you get the round of errors. You cannot have infinite precision. At one point of time, you will have a round of error. It's a classical technique, classical method, classic method. If you have a time stepping schemes, the time stepping schemes keeps the round of errors time stepping scheme keeps the round of errors from growing time step to time step. Time step to time. Let's deal with the explicit scheme. It's an unsteady diffusion equation. Explicit unsteady diffusion equation. Okay, so what was our equation? AP phi p is equal to A and B phi and B naught plus AP naught minus summation A and B. Already we have done this. Phi P naught plus B. We'll assume that there's no source term is there. It is 1D, source is 0, and for simplicity, let us take gamma is constant. Okay, gamma is constant. So how we can write this equation? AP phi P is equal to AE phi E naught plus AW phi W naught plus AP naught minus AE minus AW at phi P naught, where AE was gamma by del x t, which is nothing but gamma by del x, which will be equal to, because of uniformity, AW. And AP naught is equal to rho del B over del T, equal to, for 1D del V is del X only over del T, and that will be equal to AP because source is 0. So in the let us suppose that we have infinite precision computer. That means 0 round of error will be there. There won't be any round of error. Okay, let's assume infinite precision computer with 0 round of error. That is 5. Let us take this value 5. So that means if you put that in our option, 5p is equal to AE, no error has come, I naught plus AW, pi W naught plus AP naught minus AE minus AW pi R P naught. Okay. All right. So this is our equation 2. Let us say this was our equation 1. This is equation 2. The round of error is nothing but we have assumed that there was no round of error. But what if you don't, in practicality, we don't have a infinite precision computers? There has to be some precision. Okay. So round of error can be defined as round of error can be defined as epsilon is equal to phi minus phi. So phi can be written as phi bar plus epsilon. Put this phi back into equation 1. Okay. Put phi in equation 1. All right. So what we will get? So AP epsilon at P plus phi P is equal to AE epsilon E naught plus phi naught plus AW epsilon west naught plus phi W naught plus AP naught minus AE minus AW naught plus phi P. This is our equation 3. Now do 3 minus 2. What will you get? If you subtract both of them, what will you get? AP epsilon P is equal to AE epsilon E naught plus AW epsilon W naught plus AP naught minus AE minus AW epsilon P naught. Epsilon. This is your equation. Okay. So the round of error satisfy the original equation if you observe this equation and the original equation 1. And then they both look the same. They both look the same. Both look the same. The round of error satisfy the original equation. And we don't want this round of error to grow. Okay. Because if it will grow, then our solution will be unstable. This round of error epsilon is nothing but dependent on space and time. So if we say define a term that is amplification factor, which is nothing but ratio of epsilon of x at t plus delta t over epsilon of xt. This always must be less than equal to 1. This must be less than equal to. So now to solve this, we need to introduce a model for this round of error. So we got some round of error, which is basically a function of both space and time. Okay, it's basically a function of both space and time. So space, if you consider only x direction for 1D, for 3D it will be x, y, z. And if you are looking for in terms of stability, we have a scheme which we want to be stable. Okay, with the round of error should decrease or increase? Decrease. Should not grow from time step to time step. So if you consider a particular x, and between two time step t and t plus delta t, the ratio is the amplification vector. Okay, right. So if we can assume this composed of, in this model, if we are using, we can assume that it is composed of several modes of Fourier series. Okay, you have to see that thing. So if you are introducing a model for epsilon x comma t, it is composed of several waves that are basically a function of space and time. And we are assuming that it is in the form of exponential function or made up of cosines and sines. So how I can write this is epsilon of x of t is nothing but summation of m varying from 0 to capital M is I amx wave number and wavelength. Okay, model for the round of error. Model for round of error. This is a model for round of error, and where Km is nothing but m pi by L, m pi by L. Composed of lot of waves. If a system looks like this, we can combine all them. So it's so we can say combine all of them with single peak. You can have. Okay, we are combining all of them in the form of sines and cosines. All right. Any doubts? It is in terms of E, Km, X, and E lambda term, lambda T, where M goes from 0 to some capital M or infinite also we can take. We have introduced a model here for round of error that we get in a competition. So it is composed of several, round of error is composed of several waves in space and time that are functions of exponential. So if you think that why it is exponential, Km is the wave number, basically MP by L, M pi by L, where L is the length of the domain. If we take a length as L for the problem in one dimension. Okay. So it is composed of several waves. Each of these waves are defined by M. If you set M equal to 1, you get the one round of error, get another round of error, and so on. So that means if we are essentially trying to say if we have, let us say that the domain is of length L, we have some epsilon that is a round of error. And I would say that my round of error is something like this in the computer I'm using, or what we are saying if we are modeling this round of error using set of cosines or sines, right, as a using a Fourier expansion. And we are modeling these several waves as a linear combination of all these waves. And we can somehow represent this using a linear combination of all these things. And round of error also may grow in time or may decay in time, but we don't know. So that is why we have introduced E exponential terms, E the power of lambda mt, E to the power of lambda mt. Oh. So we have some random distribution of the round of error in the computer or the entire domain. And that distribution we are trying to approximate using several waves. That is several modes, several frequency that we have using the wave number. Okay, that is K. Okay, everything is clear. Any doubts, Manoj? Right. So now this equation is linear or non-linear? It's a linear equation. Linear because you would somehow circumvent this is on some non-linearity of the source term or diffusion by introducing additional iterations. But the resulting equation which you always get is a linear equation in Ax is equal to B form, right? All the PDs are solved get into a linear equation. Okay. So we are solving for epsilon, the error epsilon. So we have said that epsilon is composed of several modes, sigma m equals to 0 to capital M. Now, as this equation is linear, we can use the linear superposition theory because solution is linear. So summation of all these solutions. Okay. So you can apply linear superposition theory. Because equation is linear. Because equation is linear. So the simplification we are trying to get out of this is basically we do not want to look for each and every term. Okay. If we just look for one particular term for one particular m, and if that is unstable, it will make the entire system to be unstable. So we don't have to look for each and every m values. Okay. Whether we just look for one component. So suppose you are looking for some epsilon that is m of x comma t, which will be the one particular mode. That is e of m of x comma t is a thing e of I ex into of lambda t. Yes. We can look at the behavior of single term in this expansion. If one term is unstable, then whole of your solution is unstable. Right? Just a second. Mhm. Okay. So what are the grid points we have? East, west, and P for one dimension. That are characterized by x comma t. Each cell will have x plus delta x. So let me write. We have three nodes. That is P, that x comma t. E, that is x plus delta x comma t. And W, that is x minus delta x comma. Okay. For epsilon at P will be E of I k at x, E of lambda T plus delta T, right? We are basically, if I'm going back to the equation and substitute for the error terms for a single mode, we will get epsilon P, epsilon east, epsilon west, right? At time level 1, that is T plus delta T. Okay. We want to see that it doesn't grow with time. So let me write epsilon. I'm seeing this at 1. Epsilon east at 0. That will be I k x plus delta x e to the power of lambda t. epsilon best at 0, that will be eik x minus delta x e to the power of lambda t, and epsilon p at naught will be e to the power of kx e to the power of lambda t. But all these values, these are the values which you want in this equation. This equation number 4, epsilon p e naught. Put all these values. What will you get? AP e to the power of I. If you put all these values and satisfy, but we are getting e to the power of I kx e to the power of lambda t plus delta t is equal to a east e to the power of I k x plus delta x e to the power of lambda t plus aw e to the power I k x minus delta x e to the power of lambda t plus ap naught minus ae minus aw e to the power of I kx e to the power of lambda t. Okay, this is the equation we have got. Now divide using ap e to the power of I kx e to the power of lambda t on both sides. So what you will get, e to the power of lambda delta t is ae by ap e to the power of I k delta x plus aw by ap e to the power of minus I k delta x plus ap naught minus ae minus aw over ap into 1. So what is your amplification factor? Amplification factor is nothing but E at one mode x t plus delta t over E at mode m x comma t. So it is nothing but e to the power of I x e to the power of lambda t plus delta t over e to the power of I kx e to the power of lambda t. This and this cancels out. Okay. You have e to the power of lambda delta t. And you want mod of this to be less than equal to 1 for stability. Or stability. All right. Awesome. With here, everything is clear. Or any doubts? So we had this equation, which is for 1D constant gamma uniform cells with source equal to 0. We have defined AE, AW, all the terms. So if you see, AE is nothing but equal to AW is equal to gamma by delta x. AP naught was rho delta x by delta t, which is equal to AP because source is 0. So AE by AP will be gamma by delta x into delta t by rho delta x. That is gamma delta t over rho delta x square. That is equal to AW by AP as well. If you put all the in the third term, that is AP naught minus AE minus AW, this term, by AP, this term will be 1, okay? 1 minus 2 gamma delta T over rho delta X, rho delta X. All right. So if you put all these terms back into the equation, number, let's say, what was the equation number? 5. Let's give it as 5. Put in equation 5. So what will you get? E to the power of lambda t. The delta t is gamma delta t over rho delta x square e to the power of I k del x plus e to the power of minus I k del x plus 1 minus 2 gamma delta t over rho del x square. Okay. All right. So expand these terms. So e to the power of k delta x, this term can be written as 2 cos k delta x, which can be written as 2 into 1 minus 2 sine square k delta x by 2. That is, if you open up the bracket, you will get the expansion. Okay, like this. Let me write it all together. That is gamma delta t over rho delta x square 2 minus 4 n square k delta x by 2 plus your other term is 1 minus 2 gamma delta t over this term. Okay. If you observe, this term and this term will, sorry, this term will cancel out. So you will be left with 1 minus 4 gamma delta t upon rho del x square sine square k delta x by 2. And you want, this is nothing but e to the power lambda delta t, your amplification factor. You want this equal to be less than equal to 1. Okay? You want it to be less than equal to 1. Mod of this. So you can write minus 1 to 1, 1 minus 4 gamma delta t upon rho del x square, because the other term will be always be positive. Okay. So one value will come out to be 1 minus 4 gamma delta t over rho del x square is greater than equal to -1. In other cases, 1 minus 4 gamma delta t over rho del x square less than equal to 1. From here, you will get delta t is less than equal to rho del x square by 2 gamma. Okay, we have proved this. And from here, it will be 4 gamma delta t over rho del x square less than equal to 0. This is a time step criteria which you have got for the stability condition for the explicit speed, or as applied to the unsteady diffusion equation. This need to always be satisfied. Okay, for the stability condition. For explicit speed. Now you can similarly do for kinetic also, which will come out to be unconditionally stable. One another way was heuristic way. Instead of doing all this, Heuristic way will also give you the same way thing. Heuristic way. You had that coefficient which you don't want to be negative. The coefficient of 5p naught, which was AP naught minus AE minus AW. This coefficient. Okay. You want it to be positive on this. Okay. So what will you do? AP naught should always be greater than equal to AE plus AW. And you know that AP naught is what? We have written here. What is AP naught? This is AP naught. And you have written AE and AW from that. So AP naught is rho del X by delta T must be greater than 2 gamma by del X. Therefore, you can say delta T is less than equal to rho del X square by 2 gamma, which is again same as sub of equation. All right, same condition. Right. So similarly, when you will dealing with a 2D diffusion equation, you will model E epsilon of xy t is equal to e to the power of I kmx, e to the power of I kmy, and e to the power of lambda t. And for uniform spacing, you can take delta x equal to delta y. Similarly, for axisymmetric case, you can also do 2D cases also you can do. Okay? One normal stability. So in 2D, delta time step, delta t, that is the time step, is more restricted than in 1D. Okay. Now let's come to the steady diffusion and unstructured meshes. So far we have seen for the structured meshes. Steady diffusion. Next topic, steady diffusion. Unstructured meshes. So one is orthogonal unstructured and another can be non-orthogonal unstructured. Orthogonal unstructured. Second is non-orthogonal unstructured. So let's come to the orthogonal mesh cells. What do we mean? By orthogonal mesh cells, we mean that the area vector is always parallel to the line joining the cell center. Area vector is parallel to line joining cell centers. So if I have an unstructured way, unstructured orthogonal, suppose like this. Suppose I have like this. Suppose I have like this. So this is my cell of concentration. Suppose. So this has the neighboring this and this. Or let me take one more. You'll understand. Okay, let's take one more case here. Like this, if I take this as my cell of concentration. So the neighboring neighbors are this, and this. Okay, these are the neighboring cells of it. So the area vector. So what is the, and these are the cell values. Cell centroid for this, and this. So if you see, the area vector is this for the cell under consideration, and the line joining the cell centroid. Both are parallel. Both are parallel. So it's an orthogonal mesh that is parallel. The area vector is parallel to the line joining the cell centroid, and it's unstructured orthogonal mesh. Okay, unstructured orthogonal mesh. All right. Now let us disguise the equations, formulate and disguise accordingly. Just give me a minute, guys. Okay. So let me draw the mesh. So suppose so this is your cell of C0, cell centroid, and this is your cell centroid C1 for this. The line joining C0 to C1 is this. Okay, and the area vector is here, parallel. Let us assume that this is your zeta coordinate, E zeta hat, and this is E local coordinate, E NM. Right? The neighboring cells are like this, correct? This is one of the neighboring cells, C2, having a cell centroid, C2. And this is another C3. Okay, cell centroid C2. And the distance between this is theta direction, so del theta, del theta. Okay, so right here is a orthogonal coordinate system with E hat eta and En hat. Right? Our global coordinate system was this Y, A, and X. Our global coordinate system is also orthogonal. This is also orthogonal. Okay. But this is orthogonal unstructured. That earlier we used to deal with was orthogonal structure. Because there also, if you see, line joining the self-centroids is parallel to the area vector. Okay, right? Okay. So our equation was diffusion equation. Del dot uh, phi plus sp equal to 0. Integrate for the control volume. Equal to 0. Apply GDT. That will be A control surface, control volume, sp dv equal to 0. So again, how you write this? Summation over the face grad phi dot for the faces EF inner source assumption SC plus SP phi P del V equal to 0. Equal to 0. Right? This is all we have done so far in the into volume integral to surface integral using Gauss divergence theorem. Yeah, and this summation, the integration is the summation of all the face and centroid values. Okay, and linearized model. We have not done anything so far different compared to the Cartesian coordinates. Now, how do we write for this? First term, that is gamma grad phi for the face. So that will be gamma f grad phi of f. Okay. So gamma f grad phi for the global coordinate system was written as I had dou phi by dou x plus j had dou phi by dou y, right? This is that was our orthogonal system. This is also orthogonal system. We can write like this: E hat dou phi by dou zeta plus E hat dou phi by dou y. All places. And how we will write the area vector? Area vector can be written as for the global coordinate, it was axi hat plus ay j hat. But here, if you see, the area vector is pointing in only zeta direction, pointing in theta direction. So this will be a f e hat theta plus not in y direction e. Okay. All right. Now you will dot both of them. So gamma phi basis dot af is nothing but gamma f d zeta hat dou phi by dou zeta plus en hat dou phi by dou n of basis dot. Let me write there itself. AF d zeta hat. Contribution will come from this dot and dot of this. Okay. So that is gamma f AF dou phi by dou eta at basis. Okay. Now, how you write in the coordinate system that global coordinate system as dou phi by dou x, you would write as gamma del y over del x by east minus phi p in global coordinate system. Similarly, this will be the purpose of this was writing and local coordinate system was this only for the unstructured meshes that you can directly write for phi 1 minus phi naught. So gradient as phi 1 minus phi. So we will write this gradient okay, as gamma f af minus phi naught over del of. So this was spacing was del of zeta only, del of zeta, right? Okay. So again, our equation will come out to be something like AP phi p naught is equal to summation of A and B phi and B plus E, okay, where A and B is nothing but gamma f AF over del zeta of space of neighboring nodes, where NB is nothing but 1, 2, up to all the neighboring nodes you are taking. And AP is summation of A and B minus SP del V naught minus SP del V naught. B is SP del V naught. SC del V naught. Okay. I hope this is clear. Still here. Nothing is doubtful. Manoj, any doubts? Any doubts if you have, please tell. No doubts? Okay. All right. Great. I know it's a bit heavy, but if you will practice write this everything with your hand, you will find it easy. So what we can say is that it is, first we have seen what is orthogonal mesh, area vector parallel to the line joining the two cell centroids. It will not work for if the cell centroid lie outside. Okay. It will work in 3D, 3-dimensional, it will definitely work. Also, in 3D, what will happen? There will be more neighbors. Okay. It will become like a tetrahedron. So we can have a tetrahedron cell and work in 3D. Right? This equation, gamma grad phi, it's an equation of statement of conservation. We have diffusion fluxes leaving the faces and entering the facing is balanced by the source term. So again, we have statement of conservation. It will satisfy this conservation. Okay. And suppose if we have absence of source term is 0. So then it will be bounded by the neighbors. Because if you see in this equation, if this becomes 0, this is nothing but summation of A and B finally. Okay. All right. It gives you a bounded solution. Face neighbor only the face neighbor, not the other neighbors. Okay. By the face neighbor, we mean that only the face neighbor, not the other neighbors, which has a vertex in common. You can do for explicit as well as implicit scheme. When you are dealing with implicit, you have an extra term, phi p1 and phi p naught. Okay. We have done for the explicit, implicit, and canonical. You can do that thing with the structured as well as unstructured orthogonal mesh. We will not do that thing again. All right. We have a system of linear equations again. This equation. So what we can use to solve it, how we can solve this. We can solve using Gauss-Seidel or Gauss-Seidel successive over relaxation, right? To solve the system of linear equation. Can we use TDMA to solve it? No. Because we don't have a structured, right? This is not a structured mesh. So we cannot apply line by line TDMA. But of course, we can create some kind of your line and probably do it. But Gauss-Seidel is more preferred in unstructured meshes. And it has no assumptions on structure, no assumptions on structures. So if you can have unstructured mesh, but it has to be orthogonal because we have dealt with right now with the orthogonal structured mesh. Till here, we have discussed. We will discuss with non-orthogonal unstructured meshes as well in the coming tutorials. So I hope any doubts for the tutorial. That's all for today. So we have discussed a lot of things. Let's see one by one. So unsteady diffusion equation, we expanded. We have seen the explicit scheme out of it. We have seen the fully implicit method and Crank-Nicolson scheme. Then we have dealt with the truncation errors, okay, for steady diffusion and unsteady diffusion. Okay. So we came up using the Taylor series expansion. We came across with the order of accuracy with space as well as with time. All right. Okay. Then we dealt with the stability of schemes, that is non-normal stability. We dealt with the explicit undiffusion equation. Okay. We dealt about the amplification factor. We used the linear superposition theory, and we applied a model, okay, for stability. Okay. And we came out with the stability condition for explicit scheme. Similarly, with the heuristic way, also we can deal with that. Then we get towards the end of the topic, we came to the steady diffusion in unstructured meshes. First, we dealt with the orthogonal structured mesh, okay, where the area vector is parallel to the line joining the centroid values. Okay. Okay. This was all from my end. We'll see you in the next tutorial. You can leave the session. Thank you.